Hello everyone, I'm Jin Zhang from Information Retrieval Lab at Tsinghua University. Now I'm going to present our CIKM21 paper, Jointly Optimizing Query Encoder and Product Quantization. Currently, dense retrieval has achieved state-of-the-art retrieval performance by encoding documents in a low-dimensional embedding space and querying them with vector search. Despite its impressive ranking effectiveness, the retrieval cost is huge. Firstly, the size of the uncompressed embedded index is very large. It is typically an order of magnitude larger than the traditional back-of-words models. Secondly, the embedded index is usually required to be loaded into system memory or even GPU memory, whose size is highly limited. The two figures in this slide plot the effectiveness versus index size trade-off on MS Markov passage ranking and document ranking tasks. Existing dense retrieval models are bounded by the red box. It seems that the existing neural retrieval models tend to trade index size for ranking effectiveness. How can we build a compact embedding index? A direct approach is to utilize vector compression methods, an important branch of ANS algorithms. Given the encoded document embeddings, these methods quantize them to discrete vectors by minimizing the minimum squared error. However, most of these vector compression methods are unsupervised. They are task-blind and cannot benefit from supervised labels. We conduct experiments on MS Markov passage and document ranking tasks. As shown in the two figures, the commonly used compression methods, such as OPQ and LSH, significantly compromises ranking effectiveness. To enable effective and efficient dense retrieval, we propose GPQ, jointly optimizing query encoder and product quantization. As shown in the two figures, GPQ achieves competitive first-stage retrieval performance with a compact index. It is almost as effective as the uncompressed dense retrieval counterpart and also provides 30 times compression ratio, 10 times CPU speedup, and 2 times GPU speedup. Before I elaborate GPQ, let me briefly revisit product quantization, which is the foundation of our GPQ. PQ defines M sets of embeddings, each of which includes k embeddings of dimension d over M. We call them PQ central embeddings and denote them as CIG. Let D be a document embedding. Define PQ splits it to short vectors and assigns each vector to the nearest PQ central embedding. The final quantized document embedding is a concatenation of multiple PQ central embeddings. The search process is as follows. Given a query vector, PQ splits it to short subvectors. Then PQ computes similarity scores between the query subvectors and PQ central embeddings. Finally, PQ aggregates the scores with the lookup operations. The search process is highly efficient compared with the brute force search. Here I present the overview of GPQ. The top part shows PQ training procedure. The dual encoders and PQ index are separately trained. That is, the encoding, compression two steps process. The dual encoders firstly trained to minimize the ranking loss, and then PQ generates index by minimizing the MSE loss. The two-stage training is likely to make the dual encoders and PQ not optimally compatible. Besides, minimizing the MSE loss is not equivalent to improving retrieval performance. Therefore, PQ tackles these problems by leveraging an end-to-end joint optimization method. It adopts three strategies, namely ranking-oriented loss, PQ-centered optimization, and end-to-end negative sampling. Next, I will elaborate these three strategies. The first strategy is ranking-oriented loss. Previous studies used original ranking scores opted by dual encoders to compute the ranking loss. However, this score is not the actual ranking scores used by PQ for ranking, and hence introduces bias during training. To accurately evaluate the end-to-end ranking performance, ranking-oriented loss takes the input of the actual scores used by PQ for ranking. As shown in the bottom figure, the relevant scores are computed based on the quantized document embeddings. Besides, JPQ abandons the MAC loss used by PQ and only minimizes the ranking-oriented loss. This optimization object better correlates with the ranking performance. The second strategy is PQ-centroid optimization. Training PQ with ranking-oriented loss is non-trivial due to the non-differentiability and overfitting. To be specific, index assignments are not differentiable with respect to the ranking-oriented loss. Even if some methods other than gradient descent can be used to update index assignments, for example, exhaustive enumeration, it may cause overfitting problems because the number of index assignments is huge, that is, proportional to the size of the corpus. Therefore, GPQ fixes the index assignments and only optimizes PQ central embeddings with gradient descent. This optimization strategy benefits PQ index with supervised signals and helps it to evolve with the query encoder. I refer you to our paper for detailed mathematical deduction. The third strategy is end-to-end negative sampling. GPQ penalizes those top-ranked irrelevant documents to improve top-ranking performance. The theoretical foundation can be found in our CIKM paper, Optimizing Dense Retrieval Model Training with Hard Negatives. At each training step, GPQ performs end-to-end retrieval and selects top irrelevant documents as negatives. As shown in the figures, GPQ negatives are nearest to the query representation. Brute force negatives, denoted as blue crosses, are retrieved by brute force search. They do not consider the PQ and thus are not the nearest neighbors to the query vector. Finally, I'm going to present the experimental results. We use MS Markov passage and document ranking datasets. Different types of baselines are adopted, including traditional backwards methods, NLU augmented backwards methods, latent interaction models, brute force dense retrieval models, non-exhaustive NNS models, compressed NNS models. This slide shows a comparison with NNS methods. The non-exhaustive NNS methods do not compress the index and only accelerate search. Their parameters are tuned to make them as fast as GPQ. As shown in the table, GPQ still significantly outperforms them in effectiveness with a tens of times smaller index. The compressed ANS methods build compact embedding indexes. We tune their parameters to make the index size similar to GPQ's. As shown in the table, GPQ substantially outperforms them. This result strongly shows the effectiveness of our method. This slide compares GPQ with the NNS method using different trade-off settings. The left part shows the effectiveness versus compression trade-off, and the right part shows the effectiveness versus speed-up trade-off. GPQ outperforms the baselines by a large margin. The results also suggest that GPQ still performs very well with very large compression and speed-up ratio. For example, when the compression ratio is about 140 times, DBQ, the most strong baseline, incurs 28% performance loss on the document retrieval task, whereas GPQ only incurs 15% performance loss. Now we compare GPQ with existing neural retrieval models. These models do not compress index and is much more inefficient than GPQ. As shown in the table, even if GPQ compresses the index by 30 times, it outperforms by some competitive brute force dense retrieval models and gains similar retrieval performance with the state-of-the-art one. Results clearly demonstrate that GPQ effectively compresses the index with only marginal ranking performance loss. Compared with Colbert, GPQ gains similar recall with 186 times smaller index on passive retrieval task and 5,833 times smaller index on document retrieval task. In our paper, GPQ with BERT re-ranking substantially outperforms Colbert with much smaller latency. This table summarizes the retrieval speed. GPQ is as fast as back-forth models with GPU acceleration. Compared with brute force dense retrieval models, GPQ provides 10 times speedup on CPU and 2 times speedup on GPU. Compared with Colbert, GPQ provides 5 times speedup. These results highlight the efficiency of GPQ. Finally, we conduct an ablation study. We sequentially add the three strategies and can see that all three strategies contribute to the effectiveness of GPQ, regardless of different parameter settings. When fewer bytes are used to encode one document, the contribution of ranking-oriented loss is more prominent. In this situation, vectors are highly compressed, and thus optimizing the models with the actual scores used by PQ for ranking is very important. When more bytes are used to encode one document, the contribution of trained PQ parameters is more prominent, especially in terms of MR at 10. We think using more bytes to encode one document helps diversify the quantized document embeddings, and thus training central embeddings can better fit the dataset. This is all about our proposed efficient and effective dense retrieval technique, GPQ. Thank you for your listening. Contact me if you have any questions.